Hi everyone, what's up? Welcome back to my tutorial channel. Daniel's here, and today I would like to cover arithmetic and geometric progression annuities. And this is my last lesson in the series of annuities. So today first I'm going to introduce arithmetic progression annuities, then geometric progression annuity, continuous variant annuities, and palindromic annuity. So let's start off with arithmetic progression annuity. An arithmetic progression annuity is an annuity with payments that increase by a constant amount at regular intervals. So let's consider an annuity immediate with the following payments: 5, 8, 11 to 32 in years 1 to 3 to 10 at an effective rate of 5% per annum, and let A be the present value of this annuity. So A is 5V plus AV squared plus 11V cubed plus dot to 32V to the 10. So the trick to solve this annuity is we multiply both sides with 1 plus I. So 5V times 1 plus I become 5. So basically we shift everything to the left 1 unit. So now we have 1 plus I times A is 5 plus AV plus 11V squared plus dot to 32V to the 9. So now we are going to subtract the first line from the second. So we have IA. So 1 plus IA minus A is IA. 5, we have 5. 8V minus 5V is 3V, and so on. So we have 3V squared, 3V cubed, and continue to 3V to the 9. And the last term becomes negative 32V to the 10, because 0 minus 32V to the 10 is negative 32V to the 10. Now phi is a single term. The middle 9 terms, we can use level annuity immediate formula. So IA is 5 plus 3A9 minus 32V to the 10. So this is using this formula is easier for you to calculate A. So we divide both sides by I to isolate A. So A is 5 plus 3A9 minus 32V to the 10 over I. And from here we just have to plug in. I is 0.05, A9 using END mode on BA second plus calculator. V to the 10 is just 1.05 to the negative 10, and we will be able to find A. Now we are going to find a general formulas for this annuity. So I'm gonna break here I have 3A9, so I'm gonna add 3V to the 10 and subtract 3V to the 10. And I'm gonna rearrange this annuity. So I have 5 minus 5V to the 10, and we have 3A9 plus 3V to the 10 is just 3A10, and we have minus 30V to the 10. So now we are going to group the first two terms. So we have the first two terms divided by I is 5A10, and then we factor 3 out. So we have 3 times A10 minus 10V to the 10I. So this is the general formula. So now we go to the general case. In general, let P be the first payment and Q be the common difference of an annuity immediate. So the present value of this annuity is P times AN plus Q times AN minus NV to the 10 over I. So that is how we calculate the present value. for the accumulated value, basically we are going to multiply a with 1 plus I to the n, and then we derive the formula. So S become PSN plus QSN minus n over I. So I repeat, to find accumulated value. So A is a time 0, S is a time n. So basically we multiply A with 1 plus I to the n. So AN times 1 plus I to the n is Sn. 1 plus I to the n times AN is Sn. N V to the n times 1 plus I to the n is n, because V and 1 plus I cancel out. So this is the formula to calculate the accumulated value of annuity, and this is called the PIN method. So similar to annuity immediate, we also can find annuity present value and accumulated value for annuity due with increasing or decreasing payments. So remember, for annuity due, we go with double dot, and anywhere we see I, we replace it by D. So AN is annuity immediate, so for annuity due we have A double dot N. Here I will be replaced by D. And the accumulated value of this annuity is S double dot is equal to B A double dot N plus Q S N minus N over D. So to prove the present value of annuity due, we basically take the present value of annuity immediate and time with 1 plus I. We will have this formula. And for S double dot, we also take S times 1 plus I. So we have the second formulas. So this is the 4 formulas for the general case, when we don't care if P is what is P and what is if Q is positive or negative. So this is a general case, and these 4 formulas can be applied for any cases, and we say this is a PIN method. Now we consider some special cases. The increase in annuity. So let's consider an annuity immediate whose payments increase by 1 unit, 1 per unit of time, with the first payment of 1. So that means P is the same as Q, and that is 1. So we have present value as 1 AN plus 1 AN minus NV to the N over I, and that becomes A double dot N minus NV to the N over I. And IAN is just, we use this notation for increasing annuity, for this increasing annuity. So whenever you see IAN, that means this is an annuity immediate, with 1 is the first payment, and any payments after that will increase by 1. So this is a new formula. So basically, to prove this formula, we use the PIN methods and replace P by 1 and Q by 1 and to derive it. So 1 AN times I is IAN here. IAN plus AN is 1 plus I times AN, and that's become A double dot N. And also we also can calculate the accumulated value. So accumulated value, we take the present value times 1 plus I to the n, because basically present value is a times 0, accumulated value is time n. So we multiply with 1 plus I to the n and finish some basis algebra, and we have S double dot n minus n over I. And so this is annuity immediate. Now we consider annuity due. So the present of an annuity due is I double dot AN is A double dot N minus NV to N over D. So I is for immediate, D is for due. And the accumulated value is IS double dot N is S double dot N minus N over D. So that's how we find the present value and accumulated value for increasing annuity, be it due and immediate. So we have here 4 more formulas: IAN, ISN, I double dot AN, I double dot SN. So that's what it's about increasing annuity. Now we consider decreasing annuity. So consider an annuity immediate whose payment decreased by 1 per unit of time with the first payments of n. So P is n and Q is -1. So to find present value, we use pin methods, replace P by n and Q by -1, and derive it. We have n minus AN over I. And the accumulated value, and for this annuity, the present value can be notated as DAN. And for accumulated value, we should multiply the present value by 1 plus I to the n, and we have ds. N is the notation for this accumulated value. Similar for annuity due, we have D double dot A is n minus AN over D, and the accumulated value is D double dot S. So that's how we find increasing annuity and decreasing annuities. Next, the combination of increasing and decreasing annuity and level annuity. So we've been working with the general case P and Q, and we have worked with annuity, increasing annuity and decreasing annuity when P and Q are 1, 1, 1, 8, 1. So now we consider an annuity immediate at the beginning of this section using payment 5, 8, 11, 32. So by pin methods, we can find this one by using P is 5 and Q is 3. But another way to look at this, a quick way, is we first look at the common difference. So the common difference here is 3, so we immediately write out 3IA10 because it decreased by 3 units. And by this common difference, it makes the first payment only 3. So we have 369 is the corresponding annuity for 3IA10. But we need 5A and 11, so each payment we have to add 2 in addition. So we have to write out another term that is the level payment of 2, so 2A10. So the present of that value is just basically 3IA10 plus 2A10. And similar for example 2, find the accumulated value of 12-year annuity immediate with annual payments of 1,225, 2,575, and so on. So here the common difference is 1,350. So we immediately write out 1,350 IA12, and this annuity provides $1,350 in the first year, but we need only 1,225. So we need 125 less. So we write out the second term, NAPE 125 at 12. So we add the two together, we have the present value, the accumulated value. So again, for the first example, we was finding the present value, so we use A. But for the second example, we use S because this is accumulated value. Next, increase in perpetuities. Consider an increase in perpetuity immediate with payment 1, 2, 3 and continue forever. So remember, for perpetuities is just basically the limit of of annuities. So we take limit. So IA infinity is the increase in perpetuity immediate. So the limit, we take limit of IAN. IAN is A double dot N minus N V to the N over I. So now the limit of A double dot N is 1 over D. And the limit of NV to the N is 0. So we have 1 over ID is the answer for IA's infinity. IA infinity. now we're substituting d by by I over 1 plus I. This formula we learned on the lesson of measurement of interest. So we have IA infinity is 1 over I times I over 1 plus I. So we have 1 plus I over I squared. So 1 over I squared plus 1 over I. Similarly, the present value of an annuity immediate of an increasing annuity due with payments 1, 2, 3 is I double dot A infinity, and that is 1 over D squared. Some other increasing annuities. So just similar to the regular annuities, we also have annually payment annuities. So we have some other increasing annuity here when the interest is compounded with different periods of the payment. So let's say IAN, this is what we have learned, 1, 2, 3, and at the end of years 1, 2, 3 to n. So the formula is A double dot n minus nv to the n over I. Then we have this formulas IAN with the top script m. That means we have m payments of 1 over m in the first year, m payments of 2 over m in the second years. So basically each year, the first year we also paid 1 totally, but we divide it into m terms. The second years we pay $2 totally, but we divide it into m terms. So we have 2 over m for each term. So this is this formula is we replace I by I to the top script m, and formula number 3, this I top script m a top script m n. That means we pay 1 over m squared at the end of the 1 over m of a year, and there's 2 over m squared at the end of 2 over m of a year, and so on. So we have n year. At the first years, we also divide into m terms. And the first term we pay 1 m squared. The second term we have 2 m squared. To the last term of the year, we pay 1 over m, and then continue for the second years. So this is the double dot m symbol would remind us that the payments are 1 m squared, 2 m squared, and so on. But usually on the exam, we don't see this annuity regularly. So you should learn it, but it's not really important. Next, continuous payment, continuous increase in annual rate of payment at time t at t. So for continuous increase in annuity, we replace I by delta, the force of interest rate, and A double dot change to A bar. So this is continuous annuity. So that's what about arithmetic progression annuity. Now we look at geometric progression annuity. That means the payment will be either increasing or decreasing, but by percentage, not by unit. So let's consider an annuity immediate with 15 annual payments has a payment of 1,000 in the first year. Its subsequent payment increased by 3%. Find the present value of this annuity at 5.25% effective. So that means the first payment is 1,000. The second payment is 1,000 times 1.03. The next payment is 1,000 times 1.03 whole square. So now we have present value 1,000 v plus 1.03 v squared plus dot dot to 1.03 to the 14 v to the 15, where v is 1 over 1.0525. So the present value is this: 1,000 over 1.0525, 1 minus 1.03 over 1.0525 to the 15, over 1 minus 1.03 over 1.0525. So that is the answer for this present annuity. Now we consider the general case. An annuity immediate with n annual payments has a payment of 1, subsequent payment increased by a factor 1 plus k annually, and an effective rate of interest is I. So the present value is 1 minus 1 plus k over 1 plus I, the whole thing to the n, over I minus k. So this is the present value for geometric progression annuity. In all the exam, we usually have some question about geometric progression annuity. So this is also increasing and decreasing payments, but by a factor, not by a unit. Continued variant payments. So for arithmetic and geometric payments, we have the payments increasing or decreasing by units or by percentage. Now we consider a variant payments with continuous payment. So if the annual rate of payments is t a time t, the present value of the continuous increase in payment is I, it should be I bar, A bar here. N is we take integral for, we integrate from 0 to n, tv to the t dt. So we have the answer A bar n minus nv to the n over sigma. And if the annual rate of payment is ft, that means it's multiplied by ft, not t. So the present value is we integrate from 0 to n ftv to the t dt. And in the more general is when the force of interest rates is a function of t. That means we have varying for interest rates and also varying annual payments ft. So the present value here is integrate from 0 to n f of t e to the nib integrate from 0 to t delta r dr dt. Palindromic annuities. So a palindromic annuity is an annuity in which payments are read the same backwards and forwards. For example, 1, 2, 3, 4, 5, and 4, 3, 2, 1. That means whether no matter if we read it backward or forwards, we have the same payment terms. So the present value of this example is IA5. That means we drop it to after time 5. So the first 5 terms become IA5, and the last 4 is DA4, but because it starts at time 6, so we have to multiply v to the 5th. So this becomes a double dot 5 minus 5v to the 5 over I plus v to the 5th, 4 minus a4 over I. And derivatives, we have the formulas for this is a5, a double dot 5. But and by the way, if we have an annuity, this is for annuity immediate. But if we have annuity due, this becomes a double dot 5 whole square. Next, an annuity. So in general, an annuity immediate with payments of 1, 2, 3, n minus 1, n minus 1, 3, 2, 1 can be looked at as a set of n annuity with level payments of $1 each, and beginning at times 1, 2, 3, n. So the formulas for this annuity immediate is an, a double dot n. If this is annuity due, we have a double dot n, a double dot n. An annuity with payments 1, 2, 3, n minus 1, n, and another n minus 1, 3, 2, 1. So basically here is also palindromic, but n is double. So the present value of this is an plus 1, a double dot n. If we have this annuity due, then this becomes a double dot n plus 1, a double dot n. So now we work with the first problem. An annuity immediate pay 10 at the end of year 1, 20 at the end of 2 years, 30 at the end of 3 years, and so on, until the final payment 120 is made at the end of 12 years. The annual effective interest rate is 9% per year. Calculate the present value of this annuity. So the present value of this is just 10 IA12 because this is increasing annuity. So it's like 10 times IA12. And we use the formulas of increasing annuity. We have a double dot 12 minus 12 v to the 12 over I. And this becomes 393.20. So let me explain these terms. The first term is on the numerator is a double dot 12 because this is 1 minus v to the 12 over d, and d is I over 1 minus 1 plus I, so 1.9 over 1.09 is d. And use calculator, we find the answer is 393.20. Next, problem number 2. An annuity makes continuous payments, pays at a rate of 100 per year. In the first year, 110 per year in the second year, 120 per year in the third year, and so on for 10 years. The annual interest rate compounded monthly is 6%. So calculate the present value of this annuity. The force of interest rate is 0.05985. The present value is, we have here the common difference is 10, and we have the first payment is 100, so we need 90 more, so 10 I bar A bar 10 plus 90 A bar 10, and the answer is 1054.17. Problem number 3. An annuity immediate pays 500 at the end of year 1, 480 at year 2, the end of year 2, and so on, until the final payment is made at the end of 5 years. So calculate the present value. The present value here is, you see the common difference here is 20, and this decreasing. So first we write out the term 20 dA, and the first payment is 500. But if we look at this term, the first payment is just 100, so we need 400 more. So we have 485, and the answer is 1802.60. Another approach, because this is, we have only 5 years, so we can use the old methods, very simple methods. There is 500V, 480V squared, 460VQ, 440V4, and 420. This should be 420 V to the 5th, and the answer is the same. Another way to look at this is we use pin method. So P is 500, Q is negative 20, and we find the same answer. Problem number 4. A fund is built with annual payments increasing by $1 from 1 to 10, then decreasing from 1 to 0. The first payments of 1 is made today. If the fund is used to purchase a 10-year level annuity, with the first payment at 20 years from today, what is the amount of level payment? Assume an annual effective rate of interest of 4%. So the present value is, we have present value is a double dot 10 whole square. Because this is palindromic annuity, but this is annuity due. So remember, for annuity immediate, we have A10, A double dot 10. This is annuity due, so we have A double dot 10 whole square, and the answer for the present value is 71.1548. Now we use this present value to apply for another payment methods. So if we have a level payment, start 20 years from today, that means we have, if we consider time 19, is an annuity immediate of 10 payments. So present value 1.04 to need 19, x 18. So x is 18.48. Next, okay, so that is everything for today. Thank you so much for watching my video. So up to now, I have finished everything in annuities. Next lesson, I'm gonna go to chapter 5, that is investment. Thank you so much, and see you in the next video. Bye.